Guys, yesterday's lecture we have start unit number 6, optimum design. We have seen in yesterday's lecture optimum design and adequate design. Okay, also we have seen different design parameters used in optimum design. There are three parameters: preliminary design equation, it is also called as a primary design equation; subsidiary design equation, it is also called as a secondary design equation; and third is a limit equation or constraint equation. These three equations are very important: PDE, SDE and LE. Okay, also we have seen the design parameters, right? There are three design parameters: geometrical parameters, then material parameters and functional requirement parameter. With the help of some examples, we have seen that design parameters. Okay, also we have seen optimum design procedure for normal specification. In the optimum design for normal specification, first we have seen, first you have to select the geometrical parameters. Once you have fixed the geometrical parameters, decide the basic of the optimum design and write with the help of that basic PD equation, primary design equation. Also, you should write the all SDE and limit equation. Okay, secondary design equation and limit equation. Classify that parameters from primary design equation, secondary design equation and limit equation, and combine that primary design equation with secondary design equation and eliminate only the unspecified and unlimited parameters, UU parameters. Yesterday we have seen that parameters, unspecified and unlimited parameters. Okay, once you have eliminate, then using the PDE, determine the variation of optimum design quality with each parameter group. Then using that limit equation, you should calculate the secondary optimum value of each independent parameter group in primary design equation. Once you have calculated that, then from PD equation, using material parameters group, select the optimum material, and finally you should determine the optimum value of eliminated parameter using original secondary design equation, Okay, then after that also we have seen some types of the parameters: specified parameter, limited parameter, unspecified and unlimited parameters. Then after that we have seen the types of equation. There are three types of the equation we have calculated: primary design equation, secondary design equation and limiting equation. We have seen the with the help of examples. We have solved their two numericals, right? There we have solved the two numericals. Okay, then see, similar way you have to solve the third numerical. I will give the this numerical for the homework. See what is the given: design a thin walled spherical vessel for maximize gas storing capacity. Under pressure Pi is given 4 MPa. The condition is given T is less than D. T is the wall thickness and D is the mean diameter of the vessel. The factor of safety is given 3 and mass of the vessel is less than or equal to 125 gram. Design the pressure vessel with the objective of maximizing the gas storage capacity. See here you have given three materials: M1, M2 and M3. Then in that material the mass density and ultimate strength SUT and rho is given. Okay, and you know the mass of the vessel m is equal to rho into pi into d square t, and the stress induced in the vessel sigma t is equal to Pd divided by 4T. Already we have seen this equations in the pressure vessel unit number 4. Okay, our aim is designed to find D and T value for maximize capacity or storage capacity. It is denoted by the V. Means we want to calculate the volume of the pressure vessel. See, we will solve here that equation PD. First, primary design equation, gas storage capacity to be maximized. How to calculate? V is equal to 1 by 3 pi d cube. Secondary equation or second design equation, sigma t is equal to Pd divided by 4T. Okay, then you can write rearrange that equation. D is equal to P sigma T divided by 4T, and another equation, mass is equal to rho into pi d square T, because of the volume of that, okay, relation. Then you can calculate the T is equal to m divided by rho pi d square. Okay, then you should calculate the UU. Okay, how to calculate this u? Yes, anybody? You know that yesterday we have seen there is a limiting equations. Okay, m is less than m max, and sigma t is less than or equal to SUT divided by factor of safety. This value they are given. With the help of that you can find out the limiting equation. Then see the combining secondary equation with primary design equation. This is the first step. We have seen the optimum design procedure for normal specification. PD is given, V is equal to 1 by 3 pi d cube, and SD is given, D is equal to, secondary design equation is given, SDE is equal to, D is equal to P into sigma T divided by 4T. Then what is the U oblique U, unspecified and unlimited parameters. Okay, how to calculate this unspecified and unlimited parameters? This is the common parameter. T is equal to thickness, unspecified and unlimited parameter. Thickness is equal to m divided by rho into pi d square. Okay, then develop the PD equation. V is equal to, you will get m sigma t divided by 3 pi rho. Okay, put the value of D in that equation. V is equal to, then new PD equation you will get. Then limiting equation, m is less than or equal to m max, and sigma t is less than or equal to SUT divided by factor of safety. For maximization of V, m is equal to m max and sigma t is equal to SUT divided by factor of safety. This is important. The factor of safety is given 3 and m max value is given 125. Then you will get the final PD equation. V is equal to 6.944 into 10 raised to minus 6 into SUT divided by rho. Both SDE and LE are directly included, so that this is the normal specification. Before that we have seen the how to calculate the optimum design for the with the help of normal specification. Okay, then final PD we have find out. Then C will select for the material selection factor, MSF material selection factor is equal to SUT divided by rho. Okay, both value we know that rho is given and SUT also given. Rho is the mass density, SUT is the ultimate strength of the SUT. Okay, both value we know. With the help of that value you can calculate for the material 1, material 2 and material 3 material selection factor. As to maximum V, then MFS should be maximum, MSF should be maximum. Then C Mmax, M is equal to M max and sigma T is equal to SUT divided by factor of safety. Then mass of the vessel, M is equal to rho into pi into d square T. M max is equal to rho into pi into d square T, and stress induced sigma T is equal to PD divided by 4T. then you will get the one relation equating that to equation SUT divided by FOS sigma T is equal to and PD divided by 4T. Okay, then we get the result D is equal to 1.05796 meter. You can convert into mm by multiply by 1000. Then T is equal to 12.7 mm. Then V is equal to, you will get the 0.62 meter cube. V is the volume capacity of that pressure vessel. Okay guys, we have seen the some numericals on the optimum design. Definitely if you have seen in the last year question papers, you will get the one question from this on the numerical. Okay, that's why remember that three equations. That three equations are very important. First is a primary design equation, second is a secondary design equation, third is a limiting equation. With the help of that three equation, you can solve this numerical. Okay, you know how to combine that primary equation with secondary design equation, and how to make the UU equation, unsatisfied and unlimiting equation. Once you have find out that equation, then you know the limiting equation. What is the limiting condition given in your problem statement? Okay, means less than is given or less than or equal to is given. You should find out that limiting condition, means that condition should have some constant less than or equal to or greater than or equal to, okay, or less than. These symbols are used in the limiting equation. Okay, remember that. Then next we'll see the next PPT on the unit number 6. I have made some PPT again from the unit number 6. Okay, next part, all of you getting that numerical on primary design equation, secondary design equation, and third is a limiting equation. Then next part is a design for assembly, design for manufacturing and assembly. Okay, design for manufacturing. What is design for manufacturing? Already we have seen in the practical hours what is the DFM and A, okay, and DFA. Both thing we have seen. Design for manufacturing, you can make one PPT. This is given in your syllabus. Okay, you should make the PPT on that assignments topics. Okay, these topics are included. We have already covered, but I will repeat that topic here. Design for manufacturing refers to the design activity that is based on minimizing the cost of the production. Cost of the production. You should minimizing the cost of production. How to minimize the cost of the production? Or with the help of time, or with the help of market of the for the product. Okay, while maintaining an appropriate level of quality. You should maintain the quality of the product with the help of all these things, and maintain the quality of the product. A primary stage in DFM involves minimizing the number of parts in the product. Remember that the primary stage is a minimize the number of products. Means if you have the manufacturing 10 products, you should minimize that product, okay, in the 9 product. Okay, all of you getting? This is the design for manufacturing. You can made also with the help of your main project. There is one project is given, you have already done that project. You have doing the design, you have doing the manufacturing, you have drawn the all the components, you have made the assembly. With the help of that you can make the one case study on design for manufacturing and assembly. Okay, but before going on that, you know that things. Design for assembly involves making direction and methods for attaching and joining. Okay, you should you have drawn or manufactured the number of components. Okay, that components you have to assemble after manufacturing. Okay, means in that assembly involves the direction and methods for attaching and joining. You know the different methods how to attach the component, where this component you have to join, that thing you should know. The part of the product is a simpler. What is DFMA? DFMA is refers to working with both this concept together. We'll see the next. You know the benefits of the DFMA and DFA. We'll see that benefits. First is a reduce the part count. Already I have told you should reduce the part count. Means when you doing the manufacturing or assemble, then reduce the part count. Then you can easily assemble and manufacturing. Also, with the help of, if you reduce the part count, then you can reducing the cost of the product. Okay, it can be done in less time. Okay, again you have the given time. As per that time you should complete the manufacturing. So it will be the less expensive. Design for manufacturing at assembly should use as that reason, if no other. Okay, there is no any other reason. You should design for only the manufacturing and assembly. In this you will get the benefit. First is a increase the reliability. To increase the reliability, if the production process is simple, okay, there is a less opportunity of error. If the production process is complicated or number of parts are more, then you can't increase the reliability of the product, because production process is complicated again. That's why first is a, if you want to the increase the reliability, then your production process will be simple. Okay, then there is a chances of the errors is minimized. Okay, generally increase the quality of the product, right? If the product process is simple, then automatically the quality of the product will be increases. For the same reason, it again increase the reliability. This is the benefits of the DFM and DFA. Okay, design for manufacturing and design for assembly. All of you remember that the benefits. Then next we know the objective. Okay, uh, those are participant in the manufacturing as well as assembly. They know the objective. They will understand that objective before going on the manufacturing and assembly. Okay, first objective is a difference and similarities between the design. Difference and similarity between the design for manufacturing and design for the assembly. Okay, participant will know or understand the difference and similarity, okay, between the design for manufacturing assembly. Okay, then again they know describe how the product design has primary influence. Okay, they know the design has primary influence. They know the basic criteria for the part minimization. Okay, participant know the basic criteria for the part minimization, how to reduce the parts. Then again participant will understand quantitative analysis of the design efficiency. Okay, quantitative analysis of design efficiency. Then product design for easy for assembly. Yes, and last is a important of involving production engineer in DFMA analysis. Okay, this is the important objective. Once you have known the objective, or participant will understand the all the objective, then after that we'll going on the design for assembly. Okay, design for assembly already we have seen. Optimization of the parts or system we can assemble. DFA is the method design of the product for easy of the assembly. Okay, DFA is the tool used to assist the design teams in the design of products. Okay, DFA is the tool used to assist the design team in the design of products that will be transition to productions a minimum cost, focusing on the number of parts, handling and easy of the assembly. Suppose you have given the 10 parts, then you should guide to the participant how to assemble that, okay. You should focus on that number of parts, 10 parts, okay. You should handle very well and easy of assembles. Some examples we'll see after completion of that design for assembly and design for manufacturing. DFM is the method of design for easy of manufacturing of the collection of the part that will from the product after assemble, okay. Then DFA is the tool used to select the most cost effective material. Again, before going on that, for the manufacturing you should select the most cost effective material and process to be used in the production early stage of the product design. Means here is a, you should choose the correct material for the design of any manufacturing of any product, okay. The cost must be effective for that material, okay, remember that. Then what is the difference in between the assembly and manufacturing? Assembly are concerned only with the reduction of the product assembly cost, okay. Whatever may be the cost of the product, that cost will be reduced in the design for assembly. Also we can minimize the number of assembly operation, we can minimize the number of assembly operations with the help of products, okay. Also we can individual parts tends to be the more complex in design, right. These three things you should remember. Then design for manufacturing, it is concerned with the reducing overall part production cost. Production cost you can reduce with the help of DFM, okay. Also with the help of DFM you can minimize the complexity of the manufacturing operation. If there any operation is a complexity, okay, then you can minimize the complexity with the help of different manufacturing processes, okay. You can make it simple. And last is a use common datum feature and primary axis. There is a datum is given, references is given, different symbols are given, primary axis are given. With the help of that you can make it is also simply, okay. Next is a design for assembly principle, okay. We'll see one by one. Minimize the part count. First, part count should be less. Design part with a self locating features. Design parts will self fastening features. Minimize reorientation of the part during assembly. Yes, reorientation means you have to make it is a once, okay, orientation of the part during assembly. Design part for the retrieval, handling and inspection. Besides top down assembly, okay. Standardized part, minimum use of a fasteners, means you should use the standardized parts, don't use the duplicate parts, okay. Those standards parts you have to use that. Encourage modular design. Design for a best part to locate other components, okay. Means you have to show the position of that parts where this part will be fit. Design for component symmetry for inspection, this is also important, okay. DFA process, okay. Step 1, in the step 1 see what you should do in the process 1. Product information, you know the first product information, okay. Then what is the functional requirement in the product information, okay. Then once you have completed that product information, then you should go on the functional analysis of that product. Then next is a identify the parts that can be standardized, okay. You should identify the parts that can be standardized. That part should be standardized. Determine the part count efficiency. Okay, you should determine the part count efficiency. Is this having the good efficiency or part having number of counts? This is coming under the step 1. Step 2, determine your practical part count. Means practically actually how many parts are given, you should determine that. Okay, then after that identify the quality. Okay, means you have to calculate, check the is there any mistake. Okay, proving opportunity is there in that. Identify the quality means you should check the size of that, this part is fitted or not, you should check in the step number 3. Identify the handling means grasp and orientation opportunity. Okay, identify the handling, handle that part. Okay, as per the sequence, you have to check the sequence of that part. First, which is the first part, which is the second part, which is the third, which is the next part, you should and make the assemble properly. Then step 5, identify the insertion. Okay, locate and secure the opportunity. You should identify the insertion part means one by one. If there is any rod, okay, we want to the insert the rod in the given or shaft. Okay, then you have to find out the or locate the position of that shaft, where is this shaft will be fixed. Okay, in the step number 5. Step number 6, identify the opportunity to reduce the secondary operation. Again, you have to identify the opportunity to reduce the secondary operation. Means 2 times there is no any operation will do. You should identify to reduce the second operation. And last is a analyze data for the new design. And what is the guidelines for the DFA guidelines? In order to importance, reduce the part count, already I have told, and types. Ensure the parts cannot be installed incorrectly, right? Then strive to eliminate the adjustment. Okay, ensure parts self align and self locate. Ensure adequate access and unstrict vision. Ensure parts are easily handled from bulk. Minimize the reorientation, assembly in Z axis, and secondary operation during assembly. Make parts symmetrically or obviously asymmetrically. We will see the some examples. Okay, with the help of see self-locating parts. In the first figure, if you have seen, difficult to locate. Okay, there is one rod is given and another there is no any chamfer for that rod. Then where we want to the fix that part. Okay, in that second figure, see chamfers are easily located. Okay, the location we can see. If you have seen that part, then easily you can see the location of the second part. This is the self locating part. Then again, second example, see first is a difficult to locate, there is a T is given. Okay, there is no extension is given. Okay, and the size also is given less size, height is very less of that T. Okay, in that second figure, say extension axis alignment is given, properly they are touched to each other. Okay, properly they are touched to the each other, and we can insert the properly in between at the center. Then recess facilitate alignment. See again in the first figure, there is a we are doing the misalignment. In the first figure, see you can see the misalignment of the recess, but in the second figure there is a we are match the center, and you will get the complete block. Okay, this is the self locating part. There is a some example is given again. Snap fit is there, plastic bending is there, riveting is there, screwing is there. You can see this in these are all are the expensive. Okay, then in the fastening method, that means the requirement least expensive is there, fastening increasing cost. Okay, if you have taken the snap fit, the cost is less. If you have taken the plastic bending, then cost is more than the snap fit. Then riveting is there, again cost will be increased. Okay, this is the DFA and design design for manufacturing and design for assembly. Guys, I have given the one suggestion. I will give the one suggestion to you. You have done your project. Okay, you have manufacturing some parts in your project. You have designed some parts in your project. You have make the 3D model with the help of CATIA software. With the help of that, you can make the one case study. Each student will having the different case study at the time of the oral examination, because this is very important in your subject. You have given the one case study is compulsory, right? One case study is compulsory. On the basis of that, design for assembly and design for manufacturing, you can make this your own case study. Okay, today we'll stop here. Okay, all of you getting the weightage of that unit will be you have given the near 8 to 10 marks. 8 to 10 marks compulsory. You will get the one example or numerical on the basis of PDE, the SDE and limiting equation. Okay, do this also. You can do that the DFA design for assembly and design for manufacturing. Today we'll stop here. We have completed the unit number 4. Unit number I have completed unit number 4, unit number 5 and unit number 6. I have covered each and every part in my video lecture. Okay, if you have any doubt, you can message my personal WhatsApp number. I will try to solve your any query related to that subject. Thank you. All the best.